Andy.
All right, thanks, Kelly. There's the box. There we go. All right, so yeah, I'm going to do a quick review here on precipitation type in the ForecastBuilder program. But before I get too deep into that, the first thing I really want to talk about, given the main theme of what we have for today's talk, is uncertainty. If you take anything away from this, I'd actually like to take this away, is the uncertainty when it comes to precipitation type. When we look at all research for precipitation type, it's one of the challenges of doing some of this, like the statistical parts of it, is like when you're trying to correspond observations to RAOBs. You got quality issues with observations, you have RAOB drift to deal with. That quality for the observations also takes place here in the observed part. ASOS has some assumptions that take place within the present weather indicator. Oftentimes, I think it likes to switch anything sleet over to rain, or you get the unknown precip, which who knows what that is. You got AWOS doing some stuff. Maybe your OBS augmented who's doing that. MPing has, it's great to get that information, but is it still the right type? What forecast hour are you forecasting the precipitation type? And that's really important because small changes in any thermodynamic profile can lead to large changes in precipitation type. There's a specific zone that you can go from snow to freeze and rain to rain in a hurry if you don't have the thermodynamic profile forecasted just right. And then if you throw a convection on top of all of this, that can drastically change your precipitation type too. So again, just keep these factors in mind when considering precipitation type adjustments, and just think of precipitation type here too as a probabilistic distribution. I just have an example here on the right of various different distributions and that uncertainty associated with them. So in ForecastBuilder, there are 4 precipitation type techniques, and all these are being used across the NWS and within Central Region in particular for the Bourgouin one. But anyway, let me jump into these. The first one is sort of, I call it the default one, which is the top down. We have a group of offices in Central Region that are still testing the Bourgouin approach. And then we have the snow level approach for particularly the Western Region and some Central Region offices. And then there's the NBM, its output for precipitation type, and we're going to have a test bed this winter on how NBMP type works. So on the right's just a sample I took from the Northern Indiana office, just showing again how the various precipitation types are created. That's just a simple process when you're dealing with a warm air nose. This doesn't consider anything with the loss of ice in the cloud. I should note that all these 4 techniques have positives and negatives. I'll kind of discuss that. First, a quick review for the snow level calculation process. There's a lot of stuff here thrown up on the screen, but the graphic on the right is the main core to this, that you're considered all snow in the process with using snow level all the way down to about where your wet bulb is equal to 0.5 degrees Celsius. That's defined as a snow level. That's the way it is in the NBM as well. And then you drop a zone here about 800 feet, and that's a mixed rain and snow. And then you go to all rain after that 800 feet. There are some little QC checks based on some research and all that we, if the surface wet bulb is greater than 2.5 C or the temperature is greater than 45, we're just going to set everything to rain, and some other things here for surface T less than 0 C. It should be noted that just the snow level process alone will not give you any freeze and rain. In these situations, you would want to use the prob ice present grid to help get that freeze and rain, freeze and drizzle into the forecast. And then ForecastBuilder will also utilize a little sloping process to help gradually decrease the snow accumulation below the snow level. Now to get to some of the core the techniques here for P-type, the top-down versus Bourgouin, and really these 2 techniques are really analogous to lift index and CAPE. we'll kind of work through this one sample sounding and show where do these parameters fit. So the first thing that's checked on in both processes is, do I have ice in the clouds? And so you're often looking in that layer that's about -8C or colder. The next layer going down will be your max wet bulb aloft. In the case of the top down, looking at the maximum warm layer temperature. But in the Bourgouin, you're going to look at it as positive energy aloft, where you're going to compute the total amount of area there where the warm nose is above 0 degrees Celsius. Further down the sounding, we get to the cold layer. That's your bris-free sleet in the case of the top down. And the Bourgouin, it's negative energy low level. And then finally, once you get to the surface, that's you're going to utilize surface T in the top down and the surface wet bulb in the Bourgouin. Let me talk a little bit more about prob ice present, because I know this is an issue that kind of is challenging, it seems like every winter, so we'll give a little bit more about this. So the goal of what prob ice present is to help diagnose potential for drizzle environments. So one of the limiters for prob ice present that was put in quite a few years ago now was to look at the 0 to 1 kilometer RH. And if it's greater than 85%, we are gonna assign some value less, or we can assign some value less than 100 to prob ice present. Otherwise, again, it's just gonna give you 100, keeping a more snow favored environment. It utilizes aircraft data to help assign the probabilities, and the chart is displayed there to the right. Again, we really start to introduce some sort of probability ice at about -8 degrees Celsius, and then it rapidly increases to 100 by the time you get to -14, assuming a full saturation. Note that this does not incorporate vertical motion, thinking back to what I said earlier about convection. So if you have some sort of vertical motion taking place around the -8C layer, and you'd say you were dry above that, that vertical motion is going to push all that ice nuclei that is growing in the -8 and send it up at a higher temperature, the -10, -12. Basically, you're going to seed the entire cloud with ice, and then you've got snow as the main P-type. So here, with regards to the current top-down process with ForecastBuilder, this image on the right kind of displays how it works. So you're going to take raw output from each ensemble member. So let's take the NBM max wet bulb aloft grid. It's taking max wet bulb aloft of member 1, 2, 3, 4, blend them together to essentially kind of create this single composite sound, and then you get precipitation types based off of that. This process, honestly, has served us well for many years, but there are 4 problems here. In the case for max wet bulb aloft and bris-free sleet, they do not handle narrow warm cold layers well. I think a lot of you have experienced those soundings where you're just above 0, but it's over a deep layer. For example, for your warm nose, you end up with more of a liquid P-type in that scenario. We're also assuming a deterministic environment in this situation. Again, we're going to come down to one sounding to derive P-type off of. And therefore, statistically, this is very problematic. Let's say you have one sounding that's clearly snow, one sounding that's clearly rain. If you blended those together, you're going to end up with a sleet, freeze, and rain mixture, which does not exist anywhere in your distribution. It's just, your distribution is saying it's going to be snow or rain, not the in between. So you're essentially giving the wrong message to the public. So switch this over to the Bourgouin. Again, it's the same process here that we just have each member's producing some Bourgouin fields like positive energy aloft, negative energy low level. Blending those together, you get a single composite sound, and same deal. And again, Bourgouin resolves these narrow warm cold layers that I mentioned earlier because you're computing total area, but it has other problems. Again, we are assuming a deterministic environment. And a lot of this Bourgouin process, we're having to utilize a limited data set that's just within AWEPS to do this, because blending of these individual soundings is very difficult, since positive energy aloft and negative energy low level both have a bound of 0. So you can't really blend you don't have a negative value to help balance it out like you do with max wet bulb aloft. And again, statistically, this is a problem if you have a bimodal distribution. Again, you can come up with the wrong message for IDSS. So to handle some of that problem of, what's the shape of your distribution, in NBM 3.2, and it continues here for 4.0, we derive the precipitation type a little differently. So essentially, each member, kind of shown here at the top, you're going to go through the Bourgouin process, and you're going to come down and derive precipitation types here. We're also going to use surface Whipple versus T in this. Because it's in the NBM, you have a whole slew of more members that are available to you than what's in AWIPS. And therefore, through this whole process, it essentially is a more statistical and meteorologically sound approach. However, there are some operational concerns with this. How do we manipulate the precipitation types in this approach? These are now probabilistic precipitation types versus what we had before, which were more deterministic precipitation types. These precipitation type probabilities now may not mimic your temperature, like your surface temperature grid, because the surface temperature is deterministic. And so as a result, you could have freeze and rain with a temperature of 34, which I think is totally fine within this probabilistic environment. It's just a little different than what we are used to. Furthermore, with now we're going to display a whole lot of precipitation type information, there is potential for more weather keys, something we don't need of because we have that 256 limit. So what I've done here is to just take all these different approaches, put them in a little chart here where we can connect what's the science factor with the precipitation type approach. And you can see that through all this, obviously the point that we want to get to is the bottom, which is the NBM version 3.2 pouts, or with version 4.0 as well. It seems it's the best one to handle the warm cold layers, environment uncertainty, and your various distribution shapes. So our game plan this year in Central Region for precipitation type is that the offices in the probability weather type test bed will utilize the NBM precipitation type for population and begin in December 1st. Through that process, there's also going to be some testing out of this pout limiter concept, likely to help with that weather key issue, and other tools as well. Otherwise, we're not going to really have any changes from last winter. The snow level approach, being in place for the mountain WFOs. That Bourgouin approach for the Central Region testbed offices that Chicago helped develop. And again, it's great because that approach that we were testing is in the NBM when we're coming up with the actual P-type coming out of the NBM. And then for everywhere else, the legacy top-down approach will be utilized, utilizing the NBM top-down grids like Maxwell Loft, for example. And one other item here I wanted to just throw out there as a kind of a reminder is road temperature. This grid is available to you to handle impact of cold roads where you get ice in on them, because let's say you get into rain with temperatures of 35 or 36, but your roads have been really cold for the past several days because you've been underneath an Arctic air mass. Or maybe the flip side is happening where it's early season or late season, and your roads are warm, but your icing has been restricted to just elevated objects. In fact, I think this event here we had just back in October is one to reference there. These road temperature probabilities, there's some for them are come out of the MRMS, and we have them flown to you in AWIPS to help diagnose current conditions. So with that, I'm going to open this up to any questions from the field. Some contact information there available to you if you have any questions as well.